Okay, let us start our BIMS Integrable System seminar, and today our speaker is Professor Babujian in person.
Thank you. So, title of my talk is something. How was the title? Forgot you say. Factorization in deep inelastic scattering at the Björken limit and 1+1 de-integrable models. Yes. So I should first want to remind you what is the deep inelastic scattering, because we old people remember what is that, but the young generation don't know particle physics. Deep inelastic, in fact, was this scattering was the beginning of the QCD in some sense. Yes. This process was something when electron or positron scattered to proton, and then this is proton, yes, is electron. So K prime, Q square, yes. So this is a proton. So this is, that time in the 60s, they look when minus Q square very big, yes. This is usually called something deep inelastic, means this transfer of the momenta is high, you see? And then a lot of production of the particles. So this idea was something to you see this part, full CAD, yes? And this part is QCD. Because he's a proton, is electron, so just this electron is scattering here, yes? Here, this, right? So it means that here, you know 100% everything. This is because quantum electrodynamics, and here not. So with the known, and photon is the most investigated particles. So with the photon, you try to understand structure of the nucleus. This is the was idea, this always. And then pupils looking at this process and measuring this. I will write now the cross section in terms of the some four factors or structure function, and then behavior of this function from different variables. They realize the point-like structure of the protons. You see. And this was the starting point and QCD, and also the asymptotic freedom, because depending from the energies, completely was different behavior of these structure functions. Yes, I will tell you. So this the things usually is one can write something this cross section in the language of this alpha square. This because this everywhere is a charge, yes, something here. Then you have alpha square here. So Q4 and 1 minus y and F2 x Q square divided x plus y square F1 x Q square. Well, y is the just difference between electron energies, loss of energy, in fact. Yes, during the scattering. Yes. So this is and also exists the Galland-Gross relation between this F1 x square. This is a famous something process. Now also a lot of experiment exists. But so this is thing which is a four-dimensional particle physics, was in the end of 60s, and this create a lot of ideas and so on. But what was now we want to understand here? Of course, this process, everything was done using the perturbation theory, yes? But perturbation theory only working in when Q square is very big. So 2000, yes. X, yeah, okay, I forgot, you see. X is the minus Q square 2 I Q. Yes. This is dimensionless parameter, yes, X, yes, okay, thank you, I forgot. So in 2004, what? Yeah, this is correct, yeah, this is always correct. Okay, this is usually in this way people's writing. I can't do it. Yes, yeah. This is a way they like it. I don't know. This is the tradition to keep it something. Yes. So this is the something. But yes. No. Structure function. This F2. This is the cross section is amplitude something. Yes, this is a matrix element of some state. So this is the F2 and F1. This structure function. Yes, I will now write this more precise definition. This is the okay. So 2004. You see, Peter Weiss and Janos Balog. They tried to, in two-dimensional integrable models, introduce some process or some structure which is similar to deep inelastic. Yes. And this wait, you can have 2D structure function. Why not? This is some similar object. It does not mean that we have really some interaction of the particles. Of course, two-dimensional, you have asymptotic free quantum field theory, yes? ON sigma model, SON Gross-Nevin model, ON Gross-Nevin model, right? So this asymptotic free theory, but it does not mean that this really the same scattering you have as in 4-dimension. Not, but some processes one can initiate in the 2-dimension also, just like right now. Yeah? Of course, it's not the same. So in 2004, they looked such a object. They called sigma pq. Let's take some p, some state, or some is to like some g x g0 commutator mass. And then again take p. Take integral over equal x then to x. So now look, you see, this p state. So I have an integrable quantum field theory, and p state also one of the asymptotic state, one particle state. Yes. So now I have the same way as before. I have p variables and q, which is the Fourier transform of this commutator of the currents, for example, right? So it means I have q. I can range all possible ways because this is the Fourier transform, right? And p is the concrete state, some concrete momentum. So this is similar process. And then they try to calculate this object in, for example, in O3 sigma model. They have 3.4.4 factors in O3 sigma model, right? O3 sigma model. Yes. And they calculate it as they can. Yes. And then how you have to calculate? You put here 1, which is equal to theta r to 1 to infinity, yes, or 0 into infinity, and then theta r, theta 1, Yes, this is one. Yes, this is full state. So you put inside. These are asymptotical state of the integrable theory which you consider. So you put here, then come out the object which is the some gx, for example, right? And then theta 1, theta r, all right? Which is we know how to calculate in the four-factor program. Yes. So they calculate that. I will about four-factor program. He's not familiar. I will now remind you what is the four-factor program. Yes. Oleg, you know what is four-factor? No. Okay, I will tell you. So then they calculate, but most important, the conjecture they calculate in this model. Yes. Some these functions. It happens that this function at a small x, which I wrote there in x. Yes. This is like some function of x, and then another function only to square. Yes. X very small. Yeah. And this function in this O3 sigma model was this f function x was the 1 over x logarithm square x, right? Such a function they get. O3 sigma model and in 1 over n expansion in a O sigma model also. And then they make a conjecture. Paluk and Peter Weiss. Peter Weiss is his friend of Karofsky, my co-author. I forgot to tell you this paper with the Karofsky and Hrachya. Yes, Karofsky we working for 30 years.
Can I ask a question, Professor Babujian?
Yes, yes.
I have a really stupid question. I never understand the notation. Left bottom, sigma depends on p and q squared. Where is but x appeared in the right? Where is x? Here, x. Sigma depends on p and q, and where is no x in the left?
Because inside of the sigma, you can it depends from the p and q, right?
Oh, you mean Björken x, right? This is Björken x.
What?
This is Björken x. You mean like q squared divided by 2pq, right? That's a Björken x.
Okay, but also exists the 2pq also scalar product of this.
Okay. Thank you. I understand. Thank you. Sorry for interruption. I apologize.
Yeah. So then make a conjecture that this should be. Listen. So they make a conjecture. Paluk and Peter Weiss. Peter Weiss is the same person with they make the four-factor program late 70s with Karofsky. So they make a conjecture that this answer should be universal, all possible quantum field theories with asymptotic freedom. This result, yes, with small x.
Yeah, unfortunately, in the integral, you're also integrating with respect to x, but this is different x. So you
in this x, there's something different. This coordinate.
Right, I agree. That's a confusion.
I'm sorry. Okay. I can here make some other.
Right. Okay. I understand by now. Okay. Yes. I understand. That's how the x. Other x. Okay.
Can have a
I understand. Thanks.
Sorry.
Right. Why? Yes, that's much better. Now I'm happy. Thank you.
Absolutely. This is better. Yes, true. Okay. Yes. So then, so this is a conjecture. Yes. So we in our work, in some sense, we continue because they have only 3 points. If you look at the representation that they use, really remarkable something. It's a huge, several pages. These 4 factors in O3 sigma model or ON. So we have in compact some written integral representation of the 4 factors. So idea was to use the exact 4 factors to calculate this. Yes, this structure function they call. So this commutator to, for example, currents. You can arbitrary operator you can take. So this you can calculate, of course. Yes. So, of course, not easy calculation. Now we were writing big paper with details. This will be soon, I don't know, 1 month, or we will write the big paper about this. Yes. So, what is the 4 factors? Maybe I several something But this now, Andre, your question was, so this is they generate something new structure is very close ideologically to the deep inelastic process. See? So this, you see it. But what exactly we did? But you see this, where you're looking, what is this here, you see? These are currents, these electromagnetic currents. And this is the hadron currents, yes? This is quite, and then this is a structure function, two structure function we have here, yes? Yeah, so in the same we have here. So you can try, you see. Of course, this is something not exactly that you can have. This we're doing to approach the experimental curves, to understand is we going doing something wrong or it's better. So this I will show finally the result which we did with comparing with all possible experimental data from the 20 GV score to the 2000 GV score, you see. It's very impressive. So what is the four factors? I want to some small introduction to this to explain what is the four factors. Four factors, something was introduced at some, usually it was known in experimental physics, nuclear physics, yes? Four factors of some proton or some, this is a function which describes some distribution of the charge inside of the particles, yes, something. And yes, so you see the four factors are this is three. Here, let me wait. Yeah. Four factors, the matrix element of this. Mm-hmm. So this is the four factor which we mean. So physical vacuum, local operator, and asymptotical state, in or out. Yes. So late 70s was formulated starting from Polyakov, then afterwards to Peter Weiss and Karofsky, and finally Smirnov. Final answer is written question, or by Smirnov. In this reason, we call it Peter Weiss, Karofsky, Smirnov equation. Yes. This equation for this object. So this idea was if you have a S matrix, in some sense possible to recover quantum field theory. This is the subject of this bootstrap program. Yes, bootstrap program is working 3 steps. So you have first of all S matrix. Yes, you get from the Yang-Baxter equation a unitarity and crossing. Yes, crossing symmetry. So this first. Then second, you have if you have 4 factors using this 5 equation from 4-factor equation, you calculate 4 factors. It's complicated things. And third step, you put zero, yes, and calculate correlation function. It's infinite sum over something 0, phi 0, theta 1, theta n, modulus square times exponent e minus EP square. Yes. So then you calculate 2-point or n-point or correlation function. So in this way, this the subject of the bootstrap program is recovering quantum field theory using S matrix. So S matrix you calculate from the Young-Baxter. Then using this equation, you get 4 factors. Then you calculate all possible correlation function. Then the Whiteman the constructed theorem saying that if you have all possible correlation function, then quantum field theory is constructed. So this is a subject for the 4-factor program, yes? So with what we did, we last 30 years. Calculate all possible 4 factors in asymptotically free quantum field theories. So the result which we have for this, I will write for the, we have result for almost all theories, master formula we called, yes? The result of which we use for calculation today, I will show the results in 6 theories we calculate. In some sense, we classify the behavior of the small x, all possible such a theories, yes? So I will write now here the result of the 4 factors which we long time we calculate. So this is this object, yes? So we have something, yes? 5, 0, for example, yes? So n is equal to the complicated, complex contour integral in the space of some n-dimensional complex space, many. So h and p phi theta z, then is psi alpha theta and z. So this is the H function usually we get from the S matrix, because S matrix is income of the 4-factor program. This is the beta wave function corresponding the you have S matrix it means that symmetry is done. This corresponding using the S matrix you construct the beta wave function with the inhomogeneity theta. Z is this lambda parameter integrated over the complicated contours. So this formula is correct all possible integral quantum field theories. This master formula is. So this formula we examine. And P is usually called the P function. This is some exponential of the theta of Z, some polynomials. Yes. For each operator exists concrete P function, sometimes 2 even. So this is a master formula for the 4 files. So using this, one can calculate the structure function. I told you this for the current, for arbitrary operator. Yes, usually we have for each theory infinitely many operators, and then we calculate this. Look, alpha is indices because it can be this indices a lot of alpha 1, alpha n particles. These are n particles. Yes, exist here. Vector, this is yes, big, because the state have quantum numbers and so on. So this is the things which are this connected with asymptotic states, which numbers. So this is the result. Now I will write the answer that you get. So the theory is using this. Of course, this is a very complicated 4 factors. This program is usually get some people depression because answer which we have this really very complicated. Yes, because this, I think in physics, nobody calculates such a complicated because exact matrix element between physical, vacuum, local operator, and asymptotic state. So this more complicated, they're not easy to get in physics. I mean, you don't get. It's really complicated. Because all theories are massive. Yes, so it means inside of these 4 factors, you have infinite series of for example, these conformal blocks, for example. Yeah. So now I will write the result, yes, of calculation. What we observe, we put there these 4 factors. And then look the small x, is small x, variable x, yes, expansion. Then Q square is arbitrary and x is small, you see? So it means that our this sigma pq is something I will now write the answer for this theory. Yes, this is really impressive. So x again, right, minus q square divided to pq, yes? So how we calculate, I will explain in September. Next, I will come with a big paper. So then with arbitrary q square and it's x small, yes? Then we look the limit of this, we call sigma pq, right? Sigma pq. It happens that with this limit, when x small, yes, this is equal to fx and sigma, it depends only with q square. This is really more complicated object, this infinite sum of all contribution to the four factors. Yes, we say this. But this function is what the conjecture is concerning this fx function. So then we have calculated some 4 or 5 theories. So ON sigma model. Yes. So this here, fx equal to 1 over x logarithm square x. B, SUN Grosne model. Yes. Again, fx equal to 1 over x logarithm square x. Yes. C, sine-Gordon. Sine-Gordon is something very special theory. Volodya Karepin knows why. So, answer for this very something complicated to write. I will write here, yes, here. So it means it is here. X for x bigger 1 and smaller 2. And x 2 over nu minus 1, and nu is the bigger 2, smaller 4. And x again 2 over nu minus 1, then nu is bigger 4. Yes. So, and more results I have Zn and sine-Gordon. You see, the guys both have linear dependence. Something where I have to write here maybe. He's the D, A, B, C, D, sine-Gordon. Gordon again. Fx equal x just. Zn C I with E. And then fx again equal to x. Zn, this is Znizing. Okay? So we have 5 theories, you see, calculated.
But, question, can I ask you a question?
Yes, yes.
Left bottom, there is notation. So x raised power 2 divided by nu. Nu is coupling constant sine-Gordon?
Nu is, yes, exactly. Nu is the beta square divided with p minus beta square. Yes? This
and,
you love. You remember this.
Sine-Gordon. And then above, left bottom, above, I cannot see. This is x raised to power 2 nu minus 1 for when x from 2 to 4.
2 nu minus 1, yes.
Okay, thank you. Sorry for interruption. I apologize.
Yeah. So you see, this is the answer which we have, yes? Now, so this is the result of the long calculation which we did, but we long time spent to finally to to compare with the something. So in some sense, I would say that we in fact prove conjecture of the Balog and Weiss, the conjecture that one of the logarithm x logarithm square, this general universal behavior asymptotic field theory, Babujian. And then one can also have sine-Gordon very specific, because when you go to infinity, you have the SO2 steering limit. Again, we have logarithm, one of x logarithm square. You see, this is essential point. So now what we did after this, we start to, now maybe we back to our paper in Blackboard, in a file, yes. So we start to look please show the paper now. Yes. So now we will. So this calculation, of course, I will, in some details, I will explain in September, when the paper will be ready. Yes. So we something we get in 90s until 2005-6, the experimental data from the DESI. Yes. So this is the start. Until 2000 GV score exist dates. Yes. So usually they have electron scattering and positron scattering. We compare both something. This formula which they have for cross section is almost the same, because for the Q square this does not matter. Is the positron for the it's working for what is, I see. Yeah. Let's move to these pictures. Yes, something. More and more. So this is a picture which the inelastic, some nice picture. Yes, you see this is the how to calculating something already this is amplitude, and this is already the cross section. Yeah, the school of this process. More, get more. So yes, so you see, I should also take wait now here a little. I will now tell the Hrachya again, our co-author. He's expert of in the 70s. He did the Hrachya calculus. So this factorization which I wrote. So x small x, you have the function of the x and Q square. Yes. So the all time look at this picture. This picture is saying that something you see when Q square very big. It was running the string. This is a string, and then the string the interaction is so strong, and then this string is not is in some sense the cutting small pieces which create the baryons and mesons. You see, like there. But this is one-dimensional something. So it means always in this theory was in the inelastic theory was the idea that the process is the factorizing when one is time, second is the x direction of the biggest p momenta. So this is two-dimensional theory, and the other theory is three. This is the part of the something string which are making some excitation of the string. Yes, and this part is string, two-dimensional, is one-dimensional. The time. So this is a relation which we could okay, more. So now we will start to this was also in Hrachya calculus. They always write amplitudes factorized form, depend from the Q square and x. Always something you see. No, a little more. But okay, now here you see. This is the core, most essential. This picture 5. Picture 5, we looked at all the energy level. This is, look here, we start from the 15 to 90, yes? We compare, but before formula exists, one before page, even. We take one before. Even more, one more. What here? Wait, what here? Oh, wait, need more. Upstairs, more. No. Go forward. Here. Oh, here, just wait. More, little more. Here. You see, look here. So if you have this formula 4, yes? If you have the 5, you have the 4 factors which are factorized. Here. Yes, here. Function of x and q square. It means if you divide two functions with the same x and different q square, it should be something a square, q prime square, right? And then we compare with the experimental data. Now for more, Ivan, one page. So this is the picture here. After look, almost 1. So it means that in experiment, this is a result from experimental curve. That it means this factorization exists in experimental dates. That almost is 1, depending from the square momenta is very weak. Almost this 1, close to 1. This picture. So this means factorization in experimental point also is correct. It exists there. Yes, right. So now we start to compare the sine-Gordon power behavior. Only sine-Gordon has power behavior for integrable quantum field theories. Babujian. Yes. So now we compare this. You will see starting from the almost 20 GeV squared until 2000 is a fantastically very nice the fit. We make a fit. Okay, let's move forward, Ivan. The table, more. Here, so nice picture. Look here, starting from the 18. Now look the comparison of this power behavior and there's 9, all possible more. You can show until 2000. How this exactly is fit with this behavior of the sine-Gordon and the curves and this electron or positron scattering with proton. You see, so this sine-Gordon behavior is a very nice, something fitting with that. Yes, you don't get other. So this is dynamical theory with a very rich structure, right? This, of course, sine-Gordon in a nu bigger than 4. It means you have only solitons. There are no any bound state. Babujian.
So this is like a massive steering model. I say this is repulsive case when there is no bound states.
Yeah. So this is the
coupling constant in sine-Gordon fixed for some number. I mean, what's the
not fixed? Of course, you can see the fit. It ran from this coupling constant something it's gamma, of course, but you did not coupling constant gamma.
Yeah, I see that. Yes, beta square. Okay, yes, thank you.
Yeah. So this gamma is ranging from the 0 point, I don't know, some 26 to 33, 0.33. So this is some other function which is you see this function AQ square. Yes, in AQ square we have exact result for that infinite 4 factors. So this is in some sense when Q goes called go to limit go to infinity approaching what behavior something. These are some preliminary result. This is Babujian something. Yes, because this is a part which in factorized form you have a function from x and q square. This is that function. Yes, but inside of that function we have infinitely many contribution, but you can start from the first. So this is some preliminary calculation how this complicated function behavior in the case, for example, beta square equals 6.23. Yes, some concrete beta square. Yes. So Also, you see, this is starting from the 20 GV square. Exists something part of the experiment which is very poor. It means that they are only done several points from the when x is small, but q is something getting smaller, but near the 1, 0.5, or 0.100. So this part completely we don't know, something we cannot compare that. And this is because in this reason we propose with experimental pupils to, in some sense, to make more points to the fixed q square, more point x, and also many q square in order to make something this investigation more possible. Because that we believe that real strong interaction starting when q square is close to 1. Yes? And when is q square close to 1? This is the people saying usually. Even some, but always should be x square over q square should be smaller than 1. Always this caution, yes? Then our calculation will be correct. But generally, we can also look at other points also, because we have exact expression for that, yes? We can introduce arbitrary point, you can make an expansion, right? Or 4 factors. So this is the general thing which we have at the moment, and then we planning to investigate more in this other function is aq square, and try to also understand the very small q square and small x region. Yes. So this is our something result, and we next time I will explain how we calculate this all, how is procedure. This is beautiful but very complicated calculation. So this short time finished. Thank you very much. Volodya.
So thank you for your presentation.
So,
you asked me, so I ask you. You said q square equal to 1. Does it mean that the q square equal to the square of the mass of the proton? I mean, it can be, it has some dimension.
No.
Q square equal to 1, you mean that the square of the transferred moment is equal to the square of the mass of the proton? That's q equal to 1?
No. Q square is usually very big. Yes, okay. Usually until 2000 GV square. Okay. Yes.
But I mean, how it can be equal to 1? I mean,
1 when it's other direction. When you go to small and small, 1, it means there's some mass square. Yes, something small. Okay. Square is small. Yes, can be. Why not? They have some. You see, they have experiment exist, but very poor. You can see that this the DESI experiment, ZEUS and HERA, they have some region, small x and small q square. But we cannot manage to understand this structure.
Okay, thank you.
Something. This is very poor, very few points just. Yes, this is the point.
Okay, thank you.
Experiment is, in this reason, we propose the experimental people to make more x point, more q square, small, if when it's smaller, yes. Other things are okay. This is really a very nice agreements. If you see the picture of teachers, completely something very nice agreement with the power behavior. Yes. But when start, for example, this 1 of x logarithm square, when the real this strong interaction, we don't see it, you see.
Okay, yes, thank you for explanations.
Yeah, welcome. So, more question. Yes. Yeah. Yeah. Yeah, that is, yeah, they believe that is similar something. Yeah. In 4 dimension, no, this is the, of course, this is our dream to learn how we work in a 2-dimension, move to 4-dimension calculus. This, of course, would be lovely and desirable. I don't know, of course, no. But I hope, but you see, this such how to say, because you see, this result which we get is out of the perturbation theory. All result you get from exact power factors. So it means this, even the perturbation theory, you cannot calculate such a things. Not possible. Yes. So in this reason, it can be so this is will be the path to move to really that calculation which you mean. See, to learn technically, yes, to how to get such results if it's really universal. Yes, but because we don't move to still only we was in a power behavior, but in with logarithmic behavior, we should have small q square to go there. Really strong interaction. Yes, but for that region we need more points to investigate. Calculation which we can do all the regions because we have exact results. Yes, generally can do all regions. Yeah, welcome. Yeah, okay. Thank you. Thank you for Babujian to join so early morning.
Right. Thank you for explanation.
Thank you very much. Thank you very much.
Okay, we'll stay in touch by email. Thank you.
Yes,
Bye.
yes.